Today we're going to talk about solving absolute value inequalities. We saw when we solved absolute value equations, just a quick little reminder here, when we solved absolute value equations, for example, the absolute value of x plus 3 is equal to 10. We saw that we really end up getting two separate equations. Either the absolute value of x plus 3 is equal to negative 10, or the absolute value of x plus 3 is equal to positive 10. And that's because this statement says distance equals 10. And distance can be positive or negative, so this is the 10 units to the left, and this is the 10 units to the right. Now, when we talk about absolute value, we're still discussing a distance, but the idea is that our distance can be closer to or farther from that certain distance that we're talking about. So an absolute value inequality contains an absolute value expression and an inequality such as less than, greater than, less than or equal to, greater than or equal to, okay? So if I see something like the absolute value of x is less than 2, that means the distance between x and 0 must be less than 2. So let's think about this for a second. We're counting from 0, we can go 2 to the right or we can go 2 to the left. If my distance is less than 2, maybe I want to go 1.5 to the right or 1.5 to the left, or maybe I want to go 1 to the right or 1 to the left. So that's why I end up in this region here that is in between. If instead I need my distance to be greater, 2 to the right, 2 to the left, then that would mean I need to do something like 3 to the right or 3.5 to the right or 3.5 to the left or 4 to the left. And so that is why we end up moving away from the two dots. So those are our two options. When we solved compound inequalities yesterday, we saw that there was two main differences, two types of compound inequalities, either an OR inequality, that was the kind that graphed the arrows in the opposite direction. So we saw graphs that looked like this, where we shaded on either side. That means my distance is farther, which is what we just talked about. And we saw AND inequalities, and those were ones where we shaded between. We were getting closer to the center with our distances. That is going to be the big idea here with absolute value inequalities. The type of inequality, AND versus OR, is dependent on the type of inequality that you have, and that is only when the absolute value is by itself. Okay, so we have to have the absolute value by itself, then we can make a decision. So OR inequalities always come from greater or greater than or less than, so it could be this as well. And the way that I kind of remember this is I remember the word greater instead of greater. If it's a greater than inequality, it's greater, which means it's going to be an OR inequality. And then AND is when it is a less than. I kind of remember less than is an AND, so I remember the word land. That doesn't have much to do with math, but that's just kind of the mnemonic device that helps me remember. Okay? Now, when you set up an OR inequality that has a greater than symbol, you're going to set up two inequalities just the same way that we set up two equations. But I want you to notice two things that are happening. The first inequality has two flips. We flip the inequality symbol, so notice it's going less than now, and we flip the sign. So in the first inequality, it's flip, flip. Or in the second inequality, they're both the same. So the second one is keep, keep. And that's kind of what I remember in my head. Flip, flip, keep, keep with your ORs. So it's flip, flip, or keep, keep. Those are your two options. With an AND, remember we talked yesterday that another word for AND would be between. So that's easy to remember. We're always going to set this up between two less thans, okay? And if they're equal to, it'll work exactly the same. So let's look at a couple of examples. So I have on number 9, the absolute value of x plus 7 is less than or equal to 2. And so the first question is the absolute value by itself? And in this case, yes. So we're ready to make some decisions. The first thing I'm going to look at is the symbol. So I see a less than or equal to. So looking at the boxes above, less than is an and. So that is the clue that this is going to be an and inequality. So we're going to sandwich the x plus 7 in the middle. Negative 2 is less than or equal to x plus 7 less than or equal to positive 2. That's the only new part, is getting that compound inequality. From here, we're going to solve it just like normal. So I'm going to subtract 7 from all 3 spots, and I get negative 2 is less than or equal to x is less than or equal to, I'm sorry, this is not negative 2. That's going to be negative 9, and this is going to be negative 5. So there's our solution. And if I graph it, I'll have negative 9 and negative 5 solid dots since they're equal to, and we'll shade in between. Now on number 10, I cannot make any decisions yet because I have to have the absolute value by itself before I can decide if it's an and or an or. So what we should do first is subtract 1. That gives us 4 times the absolute value of 2x minus 5 is greater than 20. Then I'm going to divide by 4. And so now I have the absolute value of 2x minus 5 is greater than 5. Now that the absolute value is by itself, I'm going to look at this sign right here. And this is a greater than sign. Greater tells us this is going to be an or inequality. So here's how we set it up. Flip, flip, keep, keep. So the first equation is going to be, inequality, 2x minus 5 is flip less than flip negative 5. Or, and remember that word or is part of the notation in the symbols, 2x minus 5 keep. So keep the greater than, keep the positive 5. Those are the two things that we need. And so you can solve those equations, inequalities, add 5, we get 2x is less than 0, divide by 2, x is still less than 0. Or add 5, 2x is greater than 10, divide by 2, x is greater than 5. That's a little bit down there on the bottom, so I'll write it up here. X is less than 0 or x is greater than 5. That's our final solution. And our sketch on a number line is going to be open circle at 0, open circle at 5, and because this is an or, we're going to shade outside. Please take a second to pause the video and try number 11 and 12, and I'll be back in 3 seconds with the work and the answers. All right, we're back. So on number 11, the tricky part here is notice that this first inequality, that doesn't matter yet because the absolute value is not by itself. We have to take care of that first. And since to do that, we have to divide by negative 3, look what happens. That ends up flipping our inequality. So even though it might have looked like an or at first, it really turns out to be an and inequality. And we can solve from there, and that should be the answer that you get. Now, number 12 is interesting. Number 12 says the absolute value of x minus 11 has to be less than 0. Well, the only kinds of numbers that are less than 0 are negative numbers, and since absolute value is always positive, there are no solutions, and our graph is just an empty number line. But be careful with inequalities. We really have to interpret what we have. What if that had said less than or equal to 0? Well, then we would have to consider the case where 8x minus 11 does equal 0. It's not really an inequality. It can't be less than 0, but it can equal 0 So we would get 11/8. And on the number line, that would just look like one dot. That's the only point you can get. What if I said that that absolute value was greater than 0? Well, that would be almost all real numbers, but it does not include equal to 0. So it would look like this. At 11/8, I'd have an open circle because it's not equal to, but then the entire rest of the number line would be shaded in. And if it's greater than or equal to 0, that means it can be 0 and it can be positive. So that's every number on the number line. So be careful with zeros because it does give you some weird options. And that's where we'll stop today, and I will see you next time.